Welcome to this lesson about fundamentals of kinematics. In this video, we deal with the concept of system of coordinates, translation and rotation, and in the second part with position, velocity and acceleration. Let's begin with the system of coordinates and translation and rotation. The motion of bodies is described using system of Cartesian coordinates represented with three orthogonal vectors of unitary length, Ex, Ey, and Ez, or E1, E2, E3, depending on the convention, and a common point of application, O, which is the origin. Any point P can be univocally described as ROP equal ROO prime plus RO prime P, which means that we have the vector ROO prime, which is the vector connecting these two reference frames, and the vector RO prime P, which is the vector connecting the origin of the second reference frame with the point P. In general, we can write down that R is equal to xi, exi plus yi, eyi plus zi, ezi, which is equal also to xk, exk plus yk, eyk, and plus zk, ezk, which means that the vector r can be expressed with a coordinate in the k reference frame or in the I reference frame. In a more compact notation, we can write down that the vector r is equal to xi, yi, zi, which is equal to the component x, y, and z in the reference frame I. And also that r in the frame k is equal to xk, yk, and zk, which is equal to the components x, y, and z in the reference frame k. Both describe the same vector r, but they're usually not equal. So r in the frame I is different from r in the frame k. Let's define elementary rotation around Cartesian axis. We define the elementary rotation around the x-axis as the matrix Rx, which is equal to the matrix which column are the elementary vector of the rotated system. In this case, we have the rotation matrix X is equal to 1, 0, 0, 0 cosine of phi x minus sine of phi x, 0 sine of phi x cosine of phi x, where phi x is the angle in figure. We define also a rotation around the y-axis, which is the matrix, ROI, equal to cosine of phi y, 0 minus sine of phi y, 0, 1, 0, sine of phi y, 0, cosine of phi y. And phi y is again the angle in figure. And the rotation about the z-axis, which is the matrix RZ, cosine of phi z minus sine of phi z, 0, sine of phi z, cosine of phi z, 0, 0, 0, 1. And again, the angle phi zeta is the angle in the figure. The matrix Rx, Ry, and Rz are called elementary rotation matrices, and a combination of all these three matrices can produce any rotation in the space. In general, we can write down that the vector r in the I reference frame can be written as a rotation matrix that goes from the k reference frame to the I reference frame times the vector r in the k reference frame. Let's state some properties of the rotation matrices. We have that the rotation matrices from k to y transpose times the rotation matrix from k to I is equal to the identity. The second property is that the rotation matrix from k to I transpose is equal to the rotation matrix from k to I inverse, which is equal to the rotation matrix from I to k. The third property is that the rotation matrix from k to I of minus phi is equal to the rotation matrix of from I to k of phi inverse. And also the fourth property is that the determinant of a rotation matrix is actually equal to the cosine squared of phi plus the sine squared of phi, which is equal to 1. From property 2, we can state that the rotation matrices are orthogonal, and we can also give a physical interpretation of the property 4, which states that the determinant of the rotation matrix is equal to 1. So we can relate the property number 4 as a variation of volume. If a determinant of a matrix is greater than 1, we have an increase of volume. If the determinant of a matrix is lower than 1, we have a decrease in volume. And since our determinant is equal to 1, rotation causes no volume variation. Now we define transformation matrices. Transformation matrices are an extension of rotation matrices to consider also the translation of the two origins. So we have that a vector x expressed in the ith reference frame is equal to the rotation matrix from k to I times x expressed in the k reference frame plus the translation between the k reference frame and the I reference frame. So the vector t from k to I is the vector connecting the two origins of the reference frame. We have this transformation matrix for the x-axis, along the x-axis, which is equal to, it's a matrix 4x4, which incorporates also the translation. So the first 3x3 matrix is actually the rotation matrix. This column here is actually the translation vector along the x direction. The same is true for the y-axis. We have in the first 3x3 matrix the rotation matrix around the y-axis, and here we have the translation along the y-axis. And the z, we have the 3x3 top matrix is the rotation matrix around the z-axis, and the vector 0, 0, zt is actually the translation along the z-axis. Let's now talk about position, velocity, and acceleration. Let's now define what is a rigid body. So a rigid body is a system of pointwise masses whose reciprocal distance is constant, or can be defined also as a solid body undeformable when subjected to load or motion. In this case, we have in this figure a body which is translated, and the distance from Rx minus R minus Rx is equal to the distance R minus Rx, again in the body translated. Now we can recall the expression we derived in the first part of this lesson, which is the x referred in the reference frame I is equal to the rotation matrix from k to I of the vector x in the reference frame k plus the translation vector. So we can define the velocity. To derive the velocity, we have to redefine the vector x in the reference frame k, manipulating the expression in the first expression. So manipulating this expression, we can bring the translation vector on the left-hand side, and actually we can invert this matrix because the transpose is equal to the inverse, as we see before, and we obtain an expression for x in the reference frame k. Now we can plug this expression again in the first formulation. So now we can derive the equation, and we have that the velocity, so x dot referred in the reference frame I is equal to the r dot, which is the time derivative of the rotation matrix from k to I, of times the rotation matrix from k to I transpose times x expressed in the reference frame I minus the translation vector plus the translation vector derived. In this case, we can call this first part the product between the time derivative of the rotation matrix and the rotation matrix transpose as omega. The matrix omega is a skew-symmetric matrix, which means that the transpose of this matrix is equal to minus the matrix. So in the two-dimensional case, we have that our omega will be equal to 0 minus omega, omega 0, and in the 3D case, we have that omega will be equal to 0 minus omega z, omega y, omega z 0 minus omega x, minus omega y, omega x 0. So the velocity with respect to inertial reference frame I can be written in this form. The velocity with respect to the reference frame I is equal to omega times x in the reference frame I minus the translation vector plus the time derivative of the translation vector. The multiplication of a skew-symmetric matrix with a vector gives the same result as the cross product between two vectors. So the velocity in a fixed reference frame I is in the vector form will be expressed as the velocity with respect to the I reference frame is equal to omega in the reference frame I dot prod OP in the reference frame I plus the velocity of the translation vector, where omega is actually omega x, omega y, omega z, and OP in the reference frame I is the position of the point P in the fixed reference frame. Now let's derive the acceleration. For the acceleration, we have to derive again the velocity in the time. So we plug in the expression we already found for the velocity, and we derive this expression. After some passages, we can now obtain that the acceleration with respect to the reference frame I has this expression here. So it's the rotation matrix derived twice times the x in the k reference frame plus 2 times the first derivative of the rotation matrix times the velocity in the k reference frame plus the rotation matrix times the acceleration in the reference frame k. We can also derive the acceleration exploiting the formulation we obtained in the section about velocities. So we have that the acceleration with respect to the I reference frame is the derivative of the velocity with respect to the I reference frame, and after some passages we obtain that the acceleration with respect to the I reference frame is equal to omega dot x in the I reference frame plus omega x dot in the I reference frame times R rotation matrix dot x dot in the k reference frame plus a rotation matrix times the acceleration in the k reference frame. The lesson is over. I will give you some references for those two topics.